All right, so for example number 2 from the review, it says find the absolute maximum and minimum of f of x equals e to the cosine x on pi over 2 to 3 pi over 2. So to find the absolute maximum and absolute minimum of something on a closed interval, we need to check the value of the function at the critical numbers and the value of the function at the endpoints. So to find the critical numbers, we solve f prime of x is equal to 0. So if we take our derivative, f prime of x, the derivative of e to the x, so we can write this as f of u equals e to the u, and u equals cosine x, so we get df du times du dx gives us the derivative of e to the u is e to the u, and the derivative of cosine is negative sine. And substituting all of this out, we get negative sine x e to the cosine x for our f prime. So now we need to set that equal to 0 and solve. So we have negative sine x e to the cosine x is equal to 0. So now we use the zero product rule because we have two things that are being multiplied together. We have a negative sine x, and we have the e to the cosine x. So by the zero product rule, we have that negative sine x is equal to 0, or e to the cosine x is equal to 0. Then to solve each of these, well, we know that the exponential, this is never equal to 0. And we see that because if we tried to take the logarithm of both sides, the logarithm of 0 is undefined. So that one has no solutions. So the only one we have is this guy over here, negative sine x equals 0. So we divide by minus 1, divide by minus 1, and we get sine x is equal to 0. So then we take the inverse sine of both sides, and we get x equals the inverse sine of 0, and we get the solution that x is equal to pi times n for n being an integer. But now, since we have a closed interval, we're only worried about solutions that are between pi over 2 and 3 pi over 2. So if we did n equals 0, we get x equals 0. So that's not in pi over 2 to 3 pi over 2. If we do n equals 1, that gives us x equals pi. That is in our interval, and if we do n equals 2, we get x equals 2 pi, which now is too big, so that's not in pi over 2 and 3 pi over 2. So this is our only critical number that we have right here. So now we test the endpoints and critical numbers. So we need to calculate, well, what is f of pi over 2? What is f of pi? And what is f of 3 pi over 2? So going back to our original function, we're going to have e to the cosine of pi over 2. And the cosine of pi over 2 is 0. So e to the 0 gives us 1. And then we're going to have e to the cosine of pi. And the cosine of pi is -1. So that's e to the -1, or 1 over e. And finally, cosine of 3 pi over 2 is going to be, the cosine of 3 pi over 2 gives us 0 again, which gives us 1. So then when we look at our values, 1 over e is less than 1. These are both going to be, we're going to have a max at here and here, so at pi over 2 and 1, and 3 pi over 2 and 1, and we're going to have our min right here at pi and 1 over e. So if we grab our graphing device and we graph e to the cosine, and let's go ahead and change our window to just be from pi divided by 2 to 3 pi divided by 2. And let's go ahead and scale in 0.25s, and then let's make our min -1, our max +1, and our scale 0.1. So if we graph we get something that looks like this, and it corresponds to the values that we just talked about. So at pi over 2 and 3 pi over 2, we had our max on that interval occurred at our endpoints, and then we had our minimum, which was right here in the middle at pi, so that was our min. So on that closed interval, the extreme value theorem tells us that we're guaranteed to have an absolute max and an absolute min. And we had the absolute maxes at the endpoints, and the absolute minimum was at the critical number in the middle at 1 over e. All right, did that get your question? All right, so in example number 9 from the review, we were asked to find two numbers whose sum is 22 and whose product is a maximum. So our objective function and then we need a constraint. So for our objective function, we're told to find two numbers whose sum is 22 and whose product is a maximum. So I'm going to let my two numbers, since I'm boring, be x and y. So then my objective function is, I want their product means multiply, to be a maximum. So that gives me, my objective function is q equals x times y. My constraint is the sum is 22. So that means that x plus y has to equal the number 22. So then, as we do with all of these maximization problems, we use our constraint and we substitute it back into our original. So I'm going to solve this for y. You'll get the same number if you solve it for x and substitute back in. Everything works out just the same. So me picking y is completely arbitrary. And that gives me 22 take away x. And I substitute that back in to my objective function. And that gives me x times 22 minus x, which is negative x squared plus 22x. So then to find the maximum, we find our critical numbers. So we go q prime is equal to negative 2x plus 22. And then we solve q prime is equal to 0, so that's negative 2x plus 22 is equal to 0. We add 2x to both sides, and we get 22 is equal to 2x. We divide by 2, and we end up with x is equal to 11. Well, if x is equal to 11, I can put that back in here. Then y is equal to 22 minus 11, which is also 11. So the numbers are x equals 11 and y equals 11. And we can check, well, 11 plus 11 is 22, and apparently out of all of the numbers that add up to 22, 11 squared is the biggest number, so 121 is the biggest number that we can get. So for example 12, from the review, we want to find antiderivatives. So the key idea with antiderivatives is, remember that we are doing derivatives backwards. So for polynomials, we know that our derivative rule, when we took our derivative, d dx of x to the n was n times x to the n minus 1. So if we use that rule backwards, the antiderivative of x to the n would be, well, the opposite. To take the derivative, we brought the exponent down in front, and we subtracted 1 from the exponent. Well, the opposite is we are going to add 1 to the exponent, so x to the n plus 1, and then instead of multiplying by the exponent, we are going to divide by it. So we can apply this rule to each term in the polynomial. So our exponent is 2, so we're going to get 2 plus 1 is 3, but I forgot I have a 3 out in front, so then I'm going to get x to the third over 3 minus 2, and we do the same thing to the next one, so we get x squared over 2, and then we add 1 to our antiderivative of 7 is going to be 7x, and then don't forget your arbitrary constant plus c, and then we get a bunch of things that reduce out here. So our antiderivative, f of x, is x cubed minus x squared plus 7x plus c. So that's our rule for polynomials. For b, we need to recognize this from our derivative table. So what do we know has derivative 1 over x? Well, the natural logarithm. So our antiderivative of this is the natural logarithm of x. And we know if we take the derivative of ln x, we get 1 over x. So just remember, just like multiplication and division undo each other, or addition and subtraction undo each other, derivatives and antiderivatives undo each other. So for c, before we can do this problem, it's a little more complicated. We need to use algebra to simplify. So if we do term-wise division, we would get x squared over x squared plus 1 over x squared. So then this simplifies to, well, x squared over x squared reduces to 1 plus, and then we're going to want to use the rule that we used for a, so namely this rule, the antiderivative of x to the n. So we're going to rewrite 1 over x squared with a negative exponent as x to the negative 2. So then our antiderivative, f of x, the antiderivative of 1 is going to be x. Then the antiderivative of x to the negative 2 is we add 1 to the exponent. So negative 2 plus 1 gives us negative 1, and then we divide by negative 1 plus c. And then we simplify that up a little bit. We get x. We have a negative, and I'm going to rewrite it, put this back into the denominator, minus 1 over x plus c. So the antiderivative of x squared plus 1 over x squared is x minus 1 over x plus our arbitrary constant c. And then lastly, d is our favorite because what's the derivative of e to the x? It's e to the x. So then the antiderivative of e to the x is going to be e to the x plus our arbitrary constant. All right, so the question is, well, what would be a good guess for Newton's method? Well, the answer is, as long as it's quote-unquote close, and that's not a very good explanation right now, to the zero, Newton's method will end up working. So the answer is, if we pick pretty much any number close enough to the zero, we should be fine. So this just says find the solution in negative 10 to 5, accurate to 5 decimal places. So if we take our f of x to be our polynomial, x squared minus 10x plus 1, we can just guess something that's close to 0. So if I picked, for instance, like 5, let's just say I guessed 5, which turns out to be a terrible guess. So 5 squared is 25 minus 10 times 5 plus 1. Sorry, 5 squared. So then that's 25 minus 50 plus 1 gives me negative 24. You're like, that's not very close to 0. But if I just plug in 0 as a guess, we would have 0 squared minus 10 times 0 plus 1 equals 1. And that's going to be close to 0, because 1 is pretty close to 0. So 0 makes sense to be a good guess. But if you plug in, say, like 1, you're going to get, what, negative 8? And that's kind of close to 0, and it's probably going to work out as well. So the answer is no, it can't be any number, but it just has to be close to 0, and you can just guess. So like I guessed the first time 5, and I'm like, yeah, that's not close. So I just picked another number and tried it till I got closer to set up Newton's method. So now, to finish doing Newton's method, we need to know f prime. So f prime of x would be 2x take away 10. And then our formula for Newton's method is x sub n plus 1 is equal to x sub n minus f of x over f prime of x. So then if we put all of that in, if we substitute in, we have xn minus, then in our numerator we have x squared minus 10x plus 1, all divided by 2xn minus 10. So then, to remind us how we do this on our calculator, is we put our guess in, so we go 0 and we press enter, and then our calculator saves that as our answer, and then everywhere we see an xn, we're going to type that into our calculator as answer. So we go second, get our answer, minus, grab our fraction, And we have answer squared minus 10 times our answer plus 1 all over 2 times our answer, take away 10. When we press enter, we get 1/10. Press enter again. Press enter again. And we notice at this point, after 4 iterations, our solution didn't change at all, right? So we got exactly the same decimal approximation, so we know that it's going to be accurate to as many decimal places our calculator is. So it's accurate to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decimal places at that point. And if we really wanted to, we could check that, or at least see that it's pretty close. So I'm going to go ahead and store that in my calculator as A. So if I check this in the original now, that would be A squared minus 10 times A plus 1. If I press enter on my calculator, it indeed gives me 0. So that would be our decimal approximation of the 0 of that, and it's accurate to that many decimal places. And as we saw here, we only had to do, I think, 4 iterations of Newton's method to get the desired accuracy. All right, so for example 10, we're asked to design a cylindrical soup can that needs to have a volume of 500 cubic centimeters. If the top and the bottom cost 6 cents per square centimeter and the sides cost 4 cents per square centimeter to manufacture, what radius and what height minimize the cost of the can? So we need 2 different things for this problem. We need our objective function, and we need a constraint. So let's start with our constraint. Well, what is our constraint in this case? Well, we need to make a cylindrical soup can, and it needs to have a volume of 500 cubic centimeters. So this is telling us that V needs to equal 500. But what is V? Well, since we have a cylinder, so soup cans look like this. The volume formula for a cylinder is the area of the base, which is a circle, so pi r squared times its height has to equal to 500. So we have our radius and we have our height. So that's our constraint for this example, is that the volume of the can, so pi r squared, h has to be 500. So now what's our objective? What are we trying to minimize? So we want to minimize the cost of the can. So our cost is going to be equal to the cost of the top and bottom plus the cost of the side. All right, so we need to figure this out. So we know that the cost, and the reason I broke it up as the cost of the top and the bottom and the cost of the side is they each have different costs. So the top and the bottom cost 6 cents per square centimeter, and the side costs 4 cents per square centimeter. So to find the cost of the top and the bottom, is going to be equal to, well, it's cost per area which is going to be its cost over area times the area. because then the areas would cancel out and it would give us what we need. So we know then that our cost, which I'll just call Q now because it's our objective function. So the cost of the top and the bottom is 4 cents per square centimeter. But now we need the area of the top and the bottom. So if we look at this over here, we have our can. So the top and the bottom are both circles of radius r. So first of all, I have 2 of them. So it's going to be 2 times, and then what's our area formula for a circle? Pi r squared. So this is the cost of the top and bottom. Plus, we now need the cost of the side. Well, what is our cost for the side? Oh, I put the wrong cost in, didn't I? Cost of the top and the bottom is 6 cents per square centimeter. And then the cost of the side is 4 cents per square centimeter. But now we need to figure out, well, what's the area of the side going to be? Well, if we imagine we cut the top and the bottom off this can, then we're left with this cylinder. If I were to cut it vertically and lay it out flat, it's going to look like this, where we're going to have the height h, but then what's the width of this can going to have to be?
Circumference.
Perfect. Which is going to be 2 pi r. Perfect. So then we have one of those, so it's going to be 0.04 times our area formula, which is going to be 2 pi r times h. And that's the cost of the side. So now we simplify that. 0.06 times 2 is 0.12 pi r squared, plus 0.04 times 2 is 0.08 pi r squared h. So now we want to take the derivative of this, but it's still a function of both r and h, and that's where our constraint comes in. So we have pi r squared h is equal to
R squared for 0.08 pi r squared h.
Oh yeah, it's not r squared, it's just r, right? Because it's 2 pi r times h. Thank you. I had it correct here, and then somehow I squared it when I brought it down. Thank you for keeping me honest.
Yeah.
All right, so RH. So then we need to substitute out one of these variables. So we can substitute out r or h, but in this case, since h is linear, this is going to be the easier variable to solve for. So if we solve our constraint equation for h, we get 500 over pi r squared. And then let's go ahead and substitute that into our equation. And that's going to give us q equals 0.12 pi r squared plus 0.08 pi r times our h, which is 500 over pi r squared. So we get some things that reduce out. That r and one of our r's reduce out. And 0.08 times 500 gives us 4.
I think you only multiplied by 50.
You're correct. So 40. So 0.12 pi r squared plus 40? Yeah. 40 pi. Nope, the pi's even reduced out, right? So pi reduce out. So we get 40 over r. So now we have q equals 0.12 pi r squared plus 40 over r, and we need to find our critical number. So we take our derivative. Before we do, I'm going to rewrite this as 40r to the negative 1. So q prime is going to be 0.24 pi r. And then we take our derivatives, so the negative 1 goes out in front. Negative 1 times 40 gives me negative 40 r to the negative 2. So then rewriting this, I get 0.24 pi r minus 40 over r squared. So we set this equal to 0, and we go to solve. So 0.24 pi r minus 40 over r squared equals 0. So this is a rational function in r. So to clear our fractions, we multiply each term by our LCD, which is r squared. So we get 0.24 pi r cubed. Here, in that term, they reduce out, minus 40, and 0 times anything is 0. So now this is a cubic, so we can just isolate our r cubed by adding 40 to both sides. So 0.24 pi r cubed equals 40. Isolating r cubed, we divide by 0.24 pi. So r cubed is 40 over 0.24 pi. And finally, we take the cube root of both sides. And that gives us r equals the cube root of 40 over 0.24 pi. So then that's our radius. To find our height, we use this formula right here. So our height, h, is 500 over pi r squared. So let's go ahead and just get, those are our, so then we plug this in to get our exact answer, and then we'll get some approximations. Pi times the cube root of 40 over 0.24 pi squared. So those are our exact answers, and if we want some decimal approximations, to get our cube root, we go to our math menu and we go down to choice number 4 for our cube root, and then we have our fraction. So 40 over 0.24 pi gives us this. So that is our r value, and then to get the corresponding h value, we plug this in for r squared. So that's going to be 500, I'm doing it again, 500 over pi times our r, which we have on the previous line, so I'm just going to go second answer squared, and that gives us our two values as approximations. So that gives us our r, and that gives us our h. Sorry, those aren't strict equals, they're approximately's. So r and r. So about 3.76 centimeters for the radius, and about 11.27 centimeters for the height would be the design of the can that would minimize the cost given those constraints.